Alright, hello everybody. Hi. Okay, so what we're going to do is we're going to review the few things that we did yesterday for the object on a hill as well as the pulley question, and then we'll go from there. Okay, so this is just a recall of what we did yesterday. Alright, so I just wanted to let anybody else who's watching this video know that if you don't know what's happening in this video, I'm sorry about that. This is more for my class. So that's that. Okay. All right. Anyways, so let's say I have an object on a hill, and I have that object is standing still. Okay. So the question was, of course, what are my FBD, or what is my FBD looking like, and what are the forces that affect it? So you'll have something like this. You've got your Fn, you've got your Fg, you've got your Fgy, and you've got your Fgx. Now a few things to note: that your Fn is always perpendicular to the surface, and your Fgy is there opposing your Fn, and of course your Fgx is parallel to your surface in this situation. And yesterday what we did was we took a look at what this angle was right here. Okay, so we said, what is this angle right here? And the way that we broke it down was, if this is 20 degrees, and this is 90 degrees right here, and this is 70 degrees right here, then this right there would be 20 degrees. Okay, just from basic math knowledge that you've gained over the years. Okay. Another thing that we did yesterday was we took a look at what would happen if I allowed this box to move downward. What would be the acceleration of this box? Okay. And what we did to find out this acceleration was, we said, well, in the x direction. Now remember what we said was, my coordinate system is slanted according to the hill. So my x is like this and my y is like this. So we are using this as the y component and this as the x component. This is why we use Fgy and Fgx. I'm not using a coordinate system that's like this. Not yet. That's going to be another chapter that we're going to do that in. So we're doing that. We're changing the whole system so that it is parallel to the to my hill. It's just easier to look at. Okay, so the question was, if I had an object sliding downhill, what acceleration would this object be sliding downhill? So first thing what we're going to do is we're going to say that F net in the x direction has ma. Well, if it's got acceleration, it's got an F net, number one. So what are the forces that are in the x direction? Yes, what are they? What did we say they were? Yep. Well, we said there is no friction. So we're saying that we're allowing this object to slide down the hill. So what are my forces that exist as this object slides down the hill? Fg, which one? Fgx. Don't say Fg because there is no Fg that way. It's Fgx. So you're going to say Fgx in the x direction equals to mass times acceleration. Correct? Now your Fgx, of course, is going to be mg sine of theta, which equals to ma. And your m and your m are cancelled out, and you are left with a equals to g sine theta. Of course, g sine theta is 9.8 times sine of 20. What do you get? What is your a? What is your acceleration? How much? 3.35. Thank you very much. Meters per second squared. And of course, this will be downhill. Now remember what we said, the friction, we haven't looked at friction yet. We're not going to take a look at friction yet until in the next few days. Okay? So this would be how we would go about solving something like this. Cool? Any questions? Are we okay with this? This is what we did yesterday. Yep. Why is it Fgx equals to ma? So in the x direction, do you see any other forces besides Fgx from the FBD? Exactly. That's why it's MA. Okay? So you're literally making a system of equations, and in the x direction, there are no other forces except for that one. And that's why we made it that way. Yes? No, we're saying that the force of gravity, the x component of the force of gravity, is what causes this object to move downhill. The x component of the force of gravity is what is causing this object to move downhill. It's not gravity itself, because gravity is pulling it towards the center of Earth. But it's not moving towards the center of Earth. It's moving sideways. And that is because of the x component of gravity. Right? Any other questions? Yes? No, towards the ramp. So I mean, this one like this? That's F2y. If it's being pulled down, it's going to be the x component of gravity. If it's being pulled down, it's because of the x component of gravity. If it is going through the air, then it's just Fg. Right? If it's through the air, it's just Fg. But once it touches the hill, then it's just the x component of gravity. Right. It's a very specific question because I know a question like that. So let's leave it till we get to that section, because there is a chapter that we're going to deal with. There is a question like that in chapter 4. Yes? That would be if a hill on water? Okay. Yes, but remember, that's all dealing with friction. Here we're saying friction is negligible. Okay? So once we add friction to this, then yes, our equation is going to totally change. Until then, we're going to assume there is no friction. Yes? Here we're saying friction is negligible. Let's just avoid friction for now. And then once we introduce friction, then we'll look at it slightly differently. Okay? Okay, let me continue and go to the next one. So I'm going to erase this question. Cool? And let's do the one that we started with yesterday, the pulley question. And I had two masses. And this was mass 1. Let's say it's 8 kilos. Mass 2, let's say this is 4 kilos. And we started and said, well, first thing that we're going to take a look at in this situation is we're looking for the acceleration of the system, number 1. And we're looking for the tension in the string. Now what we said was a few assumptions that we made before we started these questions was, firstly, we're solving this as the acceleration of the system, not of the individual masses. Firstly, we're looking at it as a system. Number 2, we're saying the tension in the rope is conserved all the way through. So the tension here is equal to the tension there. Number 2. Number 3, the rope's mass is negligible and does not affect our equation. And we also said the friction between the pulley and the string, friction between pulley and string is negligible. Okay? So that's what we said. All right. And then to solve this question, we said we start with our FBD. And so you've got your FG1 pulling you down and FT upward. And here you're going to have FG2 pulling you downward and FT upward. Okay? And to solve this equation, we said we're going to make a system of equations. So you're going to see FG1 minus FT, which equals to M1A. We're making a system of equations. And here, of course, here is this gravity which is causing this object to move downward. And because it's a larger mass, and here this is the smaller mass, so here the tension is pulling that object upward. So it's going to be Ft minus Fg2, which equals to mass 2 times acceleration. We're going to add the 2. Okay, negative Ft and positive Ft cancel out. And now remember, the tension stays the same, so it does not affect our equation. And you're going to end up with Fg1 minus Fg2, which equals to mass 1a plus mass 2a. Okay, so let's do Fg1 minus Fg2 divided by m1 plus m2, which gives you acceleration. And you got your acceleration. That will be A equals to mass 1 times gravity minus mass 2 times gravity divided by mass 1 plus mass 2. Bless you. Mass 1 is 8 times 9.8 minus 4 times 9.8 divided by A plus 4. And what do you get for your A? What do you get? How much? 0.3, 3.3, 3.3 meters per second squared. Now, of course, acceleration is going to be down for this mass right here and up for that mass right there. That is the acceleration of the system. Both of my objects will have exactly the same acceleration. Okay? Now, the next thing that we're going to do once that we've figured out our acceleration is to figure out what my tension is. And to solve for my tension, I'm going to use any one of these two equations. So either I could use this equation or I could use this equation. So I'm going to say this one right here. Just say Ft minus Fg2, which equals to mass 2 times acceleration. So Ft, which equals to mass 2 times acceleration plus mass 2 times gravity, okay, which is 4 times 9.8 plus, sorry, my bad. That's going to be 4 times 3.3 plus 4 times 9.8. And what do you get for your Ft? Yes? How much? Can be 2.4. 52.4 4 newtons. So that's the tension in the string all the way through out the whole string. The tension here and the tension there is exactly the same. Yes. Yeah. How did we get this equation and this equation? Well, I looked at it and said, well, which of my two masses is causing the greater acceleration? This is my larger mass. I made an assumption that this mass is what's causing my acceleration. So in this mass, what of those two forces are greater? Well, this force is greater than that force. So that's why it's Fg1 minus Ft, which equals to mass 1 times acceleration. Here, this is Ft is larger because it's going upward. So therefore, Ft is larger than Fg2, which equals to mass 2 times acceleration. Does that make sense? You're always looking at it individually as a mass and then solving it for the whole system. Okay? Now we're going to take this equation and we're going to change it slightly and do another question. Are we okay with this? So far so good? It makes sense?